is the video lab report for the first physics lab experiment entitled Constant Velocity. The purpose of this lab was to demonstrate the effects of an environment on an object's motion by analyzing the change in velocity for an object in motion. This experiment uses velocity, the slope of a position time graph, to analyze the way the environment impacts the system. This is to test Newton's second law, which states that an object will continue in its current state of motion or rest unless influenced by an outside force. As a result of this law, this experiment demonstrates that the object must have been influenced by some outside force since the velocity is not constant. Here we take a look at Newton's second law. Force is equal to mass times acceleration. We can tell that there's force being applied to our object if our velocity changes because acceleration is being added to our mass, and is therefore giving us the force. Systems and surroundings. System is our object that we're analyzing, or group of objects that we're analyzing, and surroundings are all the forces and things that are adding to our system. For this experiment, our system was this wooden roller. Our surroundings include our hand, which gave us our initial impulse, the earth, which gave us our force of gravitation, and our table, which gave us some friction force. Figure 1. This demonstrates our first model, our observations model. This is the position. These little dots are our position over time, and this line gives us a trend line for our position. Our second model is figures 2 and 3, are depicted by figures 2 and 3. Our position versus time graph, you can see that this is a constant line with a constant velocity and is not being affected by any outside forces. So our experimental design. Our initial condition is that the object is already in motion immediately after the hand releases, meaning that we're only analyzing after the moment that the hand releases the roller. The roller is rolled across the level table, and our object's position is recorded and analyzed with our tracking software. Here is our second model code, our object, which was given a mass of 1, and our initial position vector, and our initial velocity vector. Then down here we can look at our time. We have we analyze this from 0 to 2.886 seconds, and our ball velocity, which is not increasing, meaning that there's no acceleration, and our ball position is increasing constantly. Therefore, there is also no acceleration. Now for discussion. So looking at figure 4, which compares the two sets of data, we can determine that there was an outside force acting on the system. You can see that because of this trend on our observed data, there is a fast start, which means high velocity, and then it trickles off here. Our velocity for our prediction was 0.315 meters per second, but what we ended up with was 0.2956, meaning that we started with something close to 0.315 and we ended with something less, so we have a smaller slope, meaning a less velocity, and you can see here that our prediction had a higher velocity than our observed. So what if our axes were flipped? Well, the magnitude of the slope would stay the same, but the direction would change, meaning that our speed would stay the same and the direction would be the only thing that would change. So if our object was rolling backwards or left or right, as long as it was this graph, our speed would stay the same. And what is the force being, our net force being 0 mean? So there wasn't actually a net force of 0, but it was very close to 0. Since it is a imperfect system, there is friction force applied to the object, but since it's rolling, it's very small. So for conclusions, we can say that there was some force being added to the wood, um, and that force could have been due to friction from the table or wind, and a perfect system could not be achieved without a vacuum and without gravitational forces or other forces acting on it. Some points for error could be from the tracker app malfunctioning, or, as I said previously, forces acting on our